As I have said before, the Standard Model relies on, yet lacks the ability to prove the Higgs boson, and until 2012 it was stuck like this. The theory of everything shot down by one simple assumption. Well, hardly shot down, more like put on pause. What it required was a mechanism that would give particles mass. Mass is a property of some, but not all subatomic particles. Now don't confuse mass with weight. If a particle has mass, it just means in its simplest term that the particle can be subject to the forces of nature, so its weight is a particle interacting with gravity due to the fact that it has mass. The Higgs field looks kind of like this, a grid across the entire universe. Every particle feels the field, but the amount that it interacts with the field is different. So some particles are really slowed down by the interaction of the field, like they're swimming through custard or honey, whereas some barely feel it at all. Those that feel it only a little bit have very tiny mass, something like a neutrino, and those who feel it a lot have a very large mass, something like a top-heavy quark. A little bit of trivia for you, the top-heavy quark has about the same mass of an entire atom of gold. To better understand this idea, we can kind of think of fish and water. If water was like the Higgs field, something like a fish, which is very streamlined, can swim through it with ease, barely being affected by the water at all. This is like a neutrino, where something like Barry here, Barry is not very streamlined at all and therefore will move slowly through the water. Barry is like a top quark. You can also carry on this idea about the Higgs field and the water. Once surrounded by water, you know there are no holes in the water and it is literally everywhere. This is just like the Higgs field. Now water consists of countless molecules of H2O, and it is these molecules that are like the Higgs bosons. The Higgs field is made up of tiny countless particles named the Higgs boson. So the question, why do particles have different mass? This can be phrased differently. Why do particles interact with the Higgs field differently? It's basically the same question. What we are doing is looking for patterns. Just like the periodic table, you take all the elements and order them by their characteristics. Then you find out that this group act like this, whereas this group act differently. Why? It's all because of their fundamental structure. We know why, that it's just the electron orbitals around a nuclei. But we also have our table of fundamental particles, and there are patterns in this too. Patterns that suggest that there is some kind of underlying structure that we don't understand. You can see patterns, like there are all these pairings between quarks and other quarks and leptons and other leptons, like electrons and electron neutrino. That is a pairing. But there are still a lot of things we don't know, like what is the source of this pattern? We just don't know. So we have these colliders that can smash up the particles. The magic is that what comes out doesn't have to be a rearrangement of what went in. It transforms into a quantum state of force carriers so that you can make any sort of particle that you have enough energy for. It's like trying to buy items from a shop. You have 500 giga electron volts and you can buy items up to the cost of 500 giga electron volts. This is why we need as much energy as possible in these colliders. The more energy we have, the more particles we can make. In fact, every time we raise the energy levels, we could be moving into a new area where new elementary particles are, something bigger than a top quark, for example. The point of this? One of the main things people predict is the Higgs boson, but what they think is that mass is like other characteristics of particles, like charge or spin. Some particles have it and some don't. We know this to be true as we have massless particles like photons and gluons. In fact, we can think of mass like gravitational charge, so that two particles both have mass, they both attract each other. Interestingly enough though, you can't have negative mass and so you can't have repulsive gravity. So what we can do is an experiment. We have two gluons and they come together in a collider and combine to make a Higgs boson, and then it decays into two bottom quarks, okay? So all we have to do is look for the bottom quarks that come out and then we have our Higgs boson. The problem is, two bottom quarks is the most common outcome from these collisions. It's so common that in fact we could have millions of these experiments going on and still not get the one with the Higgs boson in it, the one that we want. So instead of looking for the bottom quarks, what if we just look for the middle man? So we know what's going in and to look for what it turns into immediately, but it happens so fast and we just can't slow this down. We can literally just sit and wait to see what comes out at the other end. All that we can see is two bottom quarks that come out. And what you want to know is, did the middle stage even exist? So when we are detecting the Higgs boson, we throw a bunch of atoms into a pot and the reaction happens in 10 to the minus 23 seconds. You gather up what comes out, all the decay products, all the bottom quarks, and then you measure its weight or its total energy. Then you plot a graph of number of collisions against the total energy. You do more and more and more experiments, and then you build up your data, and then you can come up with two different theories. The first theory is that there is no Higgs boson and all the data should fall upon this line. The other is that there is a Higgs boson and all the data should fall upon this line. The problem is that the difference between the two theories is really small, and then it becomes incredibly hard to actually detect. You can compare your two theories with the data, and what you find is really you have no idea which one's true. Just because there is a tiny lump here, if this was a big lump, it would be quite easy to tell, but it's not, it is tiny. So what we need is trillions and trillions of data points. That is why the colliders run at 40 million times a second all day all year while they are on. All so we can tell the difference between these two theories. So maybe we need to come up with a new experiment, a different way of finding the Higgs. And yes, there are many different ways we can find the Higgs, and people are working around the clock on all of these theories. In fact, there are 10 different ways to make the Higgs boson. And so there are thousands of people all working on different channels, and hopefully all the data will coincide with each other, and then we have the proof that we need. Thing is, most of your mass is not from the Higgs boson or the Higgs field. Not just your mass, but everything around you, your computer, your phone, the tree across the street. Most of your mass actually comes from somewhere else. It comes from the protons and neutrons. In fact, in the proton, only about 1% of its mass is from the quarks inside using the Higgs field. So where is the rest of the mass coming from? Einstein crops up again here with his famous equation E equals mc squared, which says that we can get a lot of energy from a little bit of mass. You can then swap this around and get the amount of mass you get from a ton of energy. That is where most of the mass in the proton and neutron is coming from, and therefore your mass too. So if we pump you full of energy, you should actually weigh more than if you weren't. Einstein even said that if he had a hot cup of tea, it should weigh more than the same cup of tea cold, assuming that there is no mass lost through steam, etc. Of course, you can't measure this with a cup of tea, but this is where most of your mass is coming from, the fact that you are pumped full of energy. Now, the Higgs boson obviously has some impact on the scientific world. In the scientific world, it will validate the standard model. We will find out how certain particles acquire mass. It will help with scalar fields, which I talk about in the next video, which means that it will help us look into cosmic inflation, which then leads to possible fates of the universe. Then we have the energy of the vacuum and the cosmological constant problem. But that is all related to cosmic inflation. So it turns out that this video and the next video are quite nicely linked. However, it doesn't have any really useful applications for the common Joe on the street, unless we could find a way to make things repel the Higgs boson. I would be a bit of a bad teacher if I didn't at least try and tell you about the British theoretical physicist Peter Higgs and how he came to this theory. After all, he is one of the masterminds behind it. He is just lucky in that his name was attached to it. Both Newton and Einstein did calculations to do with mass. Newton was with weight and Einstein was with energy, but neither of them knew actually what mass was. So Peter Higgs set out to understand this. His proposal was about the broken symmetry in the electroweak theory, explaining the origin of mass and elementary particles in general, and of the W plus and minus boson and the Z boson, which, as you may remember, also have mass. His conclusion was that there is a new particle, the Higgs boson. This was then one of the most sought after particles in modern physics until the 4th of July 2012, where CERN announced that they had experimental evidence establishing the existence of the Higgs-like boson. But a lot more work needed to be done through analysis into its properties and see if it was what we expected it to be from the standard model. In fact, I actually remember where I was when they announced it too. I was at York University eating breakfast before a physics lecture, which then turned out to be about the Higgs boson, which I definitely was not prepared for. Then on the 14th of March 2013, it was announced that this new particle had zero spin as well as some other properties. These were the fundamental criteria for the Higgs boson, making it the first known fundamental scalar particle to be discovered in nature. But then bad news struck. In 2014 it was announced that there was a lot of doubt had arisen over the Higgs boson. What they said is that the two CERN teams did find a new particle, but it's not the Higgs boson. What they said is it might be an even more exotic particle. They said that the CERN data is generally taken as evidence that the particle is the Higgs particle. It is true that the Higgs particle can explain the data, but there is other explanations. They actually think that the particle they found is named the TC Higgs, which stands for the Technicolor Isosinglet Scalar. This is from one of the Standard Model competitors. It is generally believed that the Higgs boson has a mass of about 125 gigaelectron-volts. But in this other theory named Technicolor, it is believed that the Higgs boson has a much higher mass and that another particle, the TC Higgs, is believed to lie on that range. It makes sense to not at least check all the other theories rather than jumping to the assumption that it is the famous Higgs boson. So I hope you understand the Higgs boson slightly better. I know I understand it better. Just think of the fish swimming round in water, or the Higgs field, and that the water is made up of H2O molecules or the Higgs boson. But until next time.